Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the chemical potential. Let's consider a system of n identical particles with internal energy U, entropy S, and volume V. The internal energy and the function of its natural variables S, V, and N can be written as the last term is due to changes in the number of particles. This term is proportional to changes in internal energy per infinitesimal change in the number of particles when entropy and volume are kept constant. By comparing the last term to the remaining terms in this equation, we may interpret this quantity as a kind of chemical pressure or force driving the Dn or the chemical reaction the same way that T is driving the changes in entropy ds and P is driving the changes in volume dV. It is customary to represent this quantity by symbol μ and define it as chemical potential. Therefore, we have internal energy, entropy, Helmholtz, and Gibbs thermodynamic functions, and their interrelations are shown in Figure 1.6. Recall the interrelations. We have the total derivatives for entropy, Helmholtz, and Gibbs thermodynamic functions as follows. After substituting du into these equations, we get following the same way that we get the total derivative of internal energy, we can also obtain the total derivatives of these functions. They are equation D. Now, by comparing the right-hand side of equation C and equation D terms by term, along with equation A, we conclude that chemical potential can be written as this equation gives the relations for chemical potential using any of the thermodynamic functions U, H, F, or G and their specified state conditions. Among these, and for calculations related to chemical reactions of combustion, we are mostly interested in the definition of chemical potential in terms of the Gibbs function, since it is defined at a constant pressure and temperature. Now, we focus on this quantity. This is actually the total change in the Gibbs function when temperature and pressure are kept constant. Since n is a very large number, we write the amount of substances measured in the number of moles n we thus have, which shows that chemical potential is the same as molar Gibbs function. In other words, chemical potential is Gibbs function per unit mole of the substance. the concept of chemical potential is no different from that of electric potentials, or pressure as the energy per unit volume, or gravitational potential, or similar other potentials defined in physics. Now, we extend the concept of chemical potential to multi-component mixtures. The quantity can then be written as the sum of each component's contribution. Therefore, the change in the Gibbs function for a multi-component system is written as. For example, for a binary mixture, we have the last term expanded as. Okay, that's all for this task. Thank you very much, and see you next time.